This video is brought to you by us, RealPars. Join the top 1% of PLC programmers. Learn from the world's best so you can join their rank. Head on over to realpars.com and start learning now. Induction, or alternating current electric motors, rotate at a rate that is set by the number of poles inside the motor itself and the power supplied. The frequency is directly related to the revolutions per minute, or RPM, of a motor. The higher the frequency, the faster the RPM, or the higher the engine rotation speed. In the United States, electric power utilities provide alternating energy with a frequency of 60 Hz. A standard two-pole AC motor operating at this frequency provides a nominal rotation of 3,600 RPM. However, if an application does not require an electric motor running at full speed of 3,600 RPM, which is very common, a few solutions exist. 1. Using a mechanical speed reducer. It mechanically decreases the output speed by increasing torque. The output gear has more teeth than the input gear. They require lubrication, provide no flexibility, are subtle to vibration and noise, and are not suitable when shafts are distant. 2. Adding more sets of poles. It reduces the speed without altering it electrically. Currently, there are transistor systems that allow for poles inside motors to be turned on and off. However, those systems can be complex and don't provide fine control. And 3. Using a variable frequency drive. It can be configured and fine-tuned to generate a ramp, frequency, and voltage so that the motor operates according to the load requirements, that is, desired speed and voltage. An important feature of the variable frequency drive is that, as the motor speed requirements in a given application change, the drive can simply raise or lower the motor speed in order to meet new operating requirements, which would not otherwise be possible by using only the mechanical speed reducer or the transistor system to add more poles. The use of VFDs is widespread in numerous industrial and commercial applications. In industrial applications, VFDs are used to control from extruders and electric cranes to roller coasters and mechanical bowls, with so much in between. In commercial applications, VFDs are widely used in pumps to control flow and even volume in a tank, as well as in HVAC industry being considered green technology. Ultimately, a VFD varies the supplied frequency to an AC motor in order to control its speed, allowing a smooth startup and adjusting motor speed as the application requires. Now that we know why and where variable frequency drives are used, let's dive into the how does a variable frequency drive work? Let's look at this VFD diagram. The first thing we find, T3, is a current transformer, which has the function of measuring the current entering our VFD, so that the VFD controls can compare the current entering and the current leaving the VFD, measured by the two current transformers indicated by T1 and T2. If the current measured is different, the VFD will disarm due to what we call a ground fault. Following, we have the converter, also called a rectifier. If we were to expand and look at the rectifier diagram, this is what it would look like. This is called a 6-pulse rectifier or converter, and it's where the 3-phase alternating current gets converted into direct current by the use of diodes. Using an analogy of a hydraulic system, those 6 diodes can be equated to check valves. The form in which the diodes are connected with each other is very strategic. Check valves only allow flow in one direction, such as our diodes with the current flow. The electric current passes through the diode in the direction of the arrow on the diode drawing. That is, the current goes from the anode to the cathode, as shown in this image. There will only be electrical current if the voltage at the anode is greater than at the cathode. Therefore, when we connect a 3-phase alternating current to the converter, when phase A is greater than phase B or C voltages, this diode opens, allowing current to flow. When phase B becomes greater than phase A, then it is phase B diode that opens, while phase A diode is closed. And the same is true for C, as well as for the 3 diodes on the negative side of the bus. That results in 6 pulses of currents as each diode opens and closes. The resultant waveform will look like this. Next, we have the DC filter and buffer, also known as the DC bus. The DC bus is represented by only one capacitor and resistor on the diagram, but in reality, there are various capacitors and resistors associated in series and in parallel. Since the capacitors are not charged, their impedance is very low. If we were to charge them, the initial inrush could damage the input power devices, or the rectifier converter, in case the entry fuses didn't interrupt the circuit. So instead, we have a pre-charged circuit. Pre-charge is a current limiting circuit that slows the charge rate of the bus capacitors during power-up. The pre-charged circuit shown here is composed of a contact, a resistor, and a thermostat. When we energize our VFD and the bank of capacitors is not yet charged, the capacitors start to charge by the resistors. Once the VFD controls identify that the DC link is fully charged, it will then close the contact, becoming the path of least resistance for the electric current. In the scenario of the contactor not closing and the VFD still starting the motor, the current flowing through the resistor will increase, which will overheat the pre-charging resistor. The thermostat will then act, and it will disarm the VFD due to overheating. Now, let's go back to the DC bus. Its resistor function is to divide voltage, and it will guarantee that all capacitors have the same voltage. Finally, we have the IGBTs, which is the last step of the drive output, the DC to AC converter, and our PWM output. We will cover those in more detail in part 2 of the video. Summarizing what we saw today, variable frequency drives allow for precise motor speed control by varying the frequency and voltage of its power supply. There are 3 main stages to a VFD. The converter, or rectifier, composed of diodes, converts AC to DC. The DC link, composed of capacitors and resistors, filters and buffers the DC. And the IGBT module, composed of transistors, converts the DC back to AC. Today, we covered in detail the converter and the DC link. Part 2 will cover the IGBT module and how PWM allows for AC output to the motor for precise motor speed control. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.